own platform, I guess. So we have met many times. We have met many times in the past, but with different topic for me. This time I was told to review this Alice detector for you, and I will try my level best so that a clear picture of the Alice detector then and now, how they look like. And if there is any questions, please feel free to ask and stop me and ask. Okay, so the topic we will be discussing in coming 2 days will be Alice detector. But the way I will say them is detector and then Alice. And the way I will try to represent the topic is as following. I will go through a little bit about the very basics, starting from the very basic to the Alice detector. But of course, we always keep in mind that our aim is to discuss the Alice detector, whatever basic we will be discussing. Okay, so let me go back to the next slide. So here, to start with, I have given few very important variables that will be very much needed to understand this detector physics. To be more specific, even in case of our Alice detector. And I guess Professor Shao has already talked about this rapidity and all these things, but it will be better to repeat once more. So first one is the rapidity. The way I understand the rapidity is nothing but representation of the longitudinal component of the velocity in relativistic domain. Of course, the expression will be a little bit different, which is shown in the left top. So y equal to half of log E plus PL. This PL is the longitudinal part of the momentum divided by E minus PL. Now, if you approximate it to the non-relativistic limit, you will be end up with y. This rapidity is equal to the longitudinal component of the velocity. Why it is important? It is important because you know that we will be working in relativistic domain where velocity is not a invariant quantity. So it's better that we will represent our information in such a way that things will be rather invariant or rather look similar, look similar when we say something. And in that sense, instead of using velocity, rapidity could be a good variable. And you will see later on that whenever we talk about the detector extension, we never talk in terms of how much velocity it will cover, rather we will talk about how much rapidity it will cover, apart from other variables. So please keep in mind that rapidity is used to communicate the extension of the detector or the extension of the reach of any physics information that people will discuss in this domain. Then comes the luminosity. This is very much important, not from the kinematic point of view only, but also from the detector point of view. Since we will be understanding the Alice detector, it's a complex detector, and it is built for a specific purpose to serve the data collection and the processing, and which will be delivered by the LHC. We need to understand how much particles we are really expecting to be detected by our detector. Okay, and then and the important quantity is the luminosity. So luminosity is what? So this gives you basically, this is sort of a interrelating quantity between the cross section and the number of interactions per time. And if you look at this expression for this capital L, which is the luminosity, it contains the number of particles, number of particles in a beam coming from, say, left side, and other n is the number of particles coming from the other side, say right side. So number of particles containing in the two beam coming from opposite directions, which will be colliding, those are represented by n1 and n2. And what is the f? F is you can take it as the number of interactions. Okay, so this is sort of number of collisions that you will expect when these two beam will be crossing. One should not say to be specific this beam, rather one should say these as bunch. bunch of particles. So beam are not continuous in LHC ring, they are coming as bunch. So one bunch, then some gap and another bunch. So when we are talking about this luminosity, it means two bunches coming from opposite directions having N1 and N2 number of particles colliding each other with a probability of number of collision F, and there is a cross section for them. So it is not that all the particles will be colliding. There should be some cross sections for this collision, and this cross section is represented by the capital A. And this is important, very much important. Why? Because when you design a detector, you have to keep in mind that, okay, this is the experiment, and in this experiment, this many particles will be delivered by the machine. And out of this many particles, this many interactions I am expecting, and from each interactions, I will have, say, 10 or 20 or 100 or 1,000 particles, and accordingly, I need to segment, I need to design, I need to build my detector. And from that point of view, this luminosity is equally important. You have to keep in mind. And then minimum ionizing particle. Again, I try to keep it here specifically for a reason, since we are discussing detector. So you know that whenever you are building a detector, you have to keep in mind that there should be a limit between which your detector should work. And how this limit are set? The lower limit should be it should be capable of measuring the lowest possible energy deposited by an particle, which is represented by the MIP. And I guess that you all are aware about this Bethe-Bloch formula. If you look at the Bethe-Bloch formula, you can put a condition that energy loss by the collision equal to the energy loss by the radiation, and what the result you will be landed with is corresponds to the energy deposition for a minimum ionizing particle, which is at the deep, where from left side your Bethe-Bloch formula decrease and at a minimum value, and then again increase due to the radiation. So I'm talking about this minimum amount of energy deposition. So your detector should be such that it should respond to the MIP. And why I am spending so many words? Because you know that whenever you will be building some detector, it will be faced with some electronics. There will be a lot of surroundings to your detector. They may contribute a lot of noise when you are picking up. Okay, so the detector should be capable of to discriminate this minimum amount of energy deposition, meaningful minimum amount of energy depositions from this background contribution. Okay, in that sense, this MIP is very much important to understand when you are building detector. Okay, and then comes the material budget. So what is material budget? It is, as it is, the name itself suggests, it relates to the amount of material the detector itself containing or might facing before it, okay, or surrounding it. Surrounding it is has also importance because there may be a lot of multiple interactions as well. And usually these material budgets are represented in terms of radiation length. And the expression is something like this. I'm a little bit sure that you all are aware about all these four variables, but for the sake of very frequent use in the later part of my presentation, I thought to bring to your notice in the early. Okay, then as I have said that before going to Alice, let us discuss detector. Very basic one. What is detector? Detector is an arrangement which tells about some incidents, identity of the incidents, and maybe other kinematic information in terms of some measurable observable. Please keep in mind this measurable observable means a lot. It may be energy deposition. Energy deposition is always will be there in your detector, but it will be generated, it will be reflected in some other way. It may be a light, so energy deposited in your detector, and it will come to you not as direct energy deposition, maybe as a collection of charge, or maybe a bunch of light photon, or something like this. So in that sense, detector should be some arrangement taking either liquid or gas or solid, connected to some proper arrangement of readout mechanism, which will able to give you the information about some particle incidence or its identity, whether it's a electron, it's a photon, or it's a proton or pion, etc. And if they are detected, what are their kinematic information like momenta, positions, energy, and so on. And the simplest possible, I mean, this detector can be very simple or it can be very complex. The simplest possible detector that I can think about is the, schematic I have shown in the left side. This is this is your MSc time, most probably lab experiment. You might have experienced this kind of experiment in your lab. So this is a typical example of a Geiger-Müller counter, but let's not talk about Geiger-Müller counter. Let me take it as a simple tube, which, the wall of, whose wall is acting like a electrode, and insert a wire along the central axis. And let us assume is that it has anode. Fill this tube with a gas. Now, throw a very high energy particle. Let us assume it's an electron or some other charge particle. Why charge particle? We will come to it later on. And when this charge particle passes through this gas tube, it has, if the energy is high enough, it can knock out one electron of the gas molecule. So essentially, it will produce an ionization. Once this ionization produced, this means positive ion and electron, negative electron will start moving towards the anode wire, central wire. Now, you know, because of the cylindrical geometry, around the axis, central axis, the field will be very high even for a comparatively low voltage applied across this anode and cathode, right? So if the field is enough, then, in the close vicinity of this anode wire, this electron will start accumulating more and more amount of energy. And when the energy is high enough, then again it can produce more ionization in the gas. And so it will form secondary charge. So essentially it will avalanche. It will produce second generation of charge particle, and next one will produce third generation of charge particle. So like a tiny cluster. And this cluster will move toward the anode wire, right? And what about this anode, these ions, positive ions, they will start moving in the opposite direction. Now, during this movement, if you look at the, if you have some way to collect some informations, electrical charge, which can collect the electrical charge, and then you will see during the movement of this charge, you will find this spike, which essentially represents the current pulse. So what does it tells you? So a charge particle moving inside the gas, ionizing it. So it is leaving a footprint of its passing through the gas volume, and essentially leaving a signal which you are detecting. Just give me a moment. A phone is there. Hello. Hello. Jubeda. না এর তনয় বোধহয় ফোনটাই ওয়াশরুমে রেখে চলে গেছিল, আমাদের একজন দিয়ে গেল আমার রুমে, ওকে একটু বলে দিই কোনোভাবে। Sorry for the interruption. Yeah, so the simplest detector is a very simple gas tube, with a voltage applied across the wall and the anode wire. And this simplest detector is actually used in real-time experiments, like and they are designed to serve a specific purpose. It may be maybe to detect the a particle entering, reaching a particular level, or sometimes if you want to measure energy of this particle, probably you have to arrange not a single one, but many of such kind of detectors in a stack, so that you can measure their energy. So this is the simplest case. What if you have a little bit complex situation? And complex situation could be in the simplest case I was talking about, a single particle with a single energy is coming toward you, and you wanted to measure it. But what happens if you have number of particles having a wide energy range, starting from MeV, sometimes say EV, EV to GeV. And you can always expect detection mechanisms cannot be same for EV range or KEV range or MeV range or GeV range. You need to adopt different type of detection mechanism when you have a wide energy range of particles. This is sure. And not only this, you never expect that maybe, not only the energy are different, maybe the particles which are coming towards you, they may have of different kind. They may have different masses. They could be electron, proton, on neutron, gamma, etc. And they may have different charge states as well. If they are ion, yes, sorry, someone is asking something. Okay, it seems it's a noise. Okay. So particles not only have their energy different, they may be of different identity. They may have different masses. They may have different charge states. And not only that, these particles not necessarily will come from a particular directions. They can come from various directions. Right. So now, if your particle source is at a particular point, and you don't restrict the particle to eject in any directions, you can expect, because of this randomness of any, say, radioactive source, it can emit in any directions. And if you are there enough to, make an arrangement so that each and every particles you want to detect, then probably you will need a detector system, something like this, as I have shown in the right side. But though I have, showing you in the 2-dimension, but please keep in mind, if particles are, coming from any direction, or particles are coming out from a point in any directions, we have to place this number of blocks of different kind in all 4 pi direction, not only in single directions. For the sake of understanding, I have sketched here in one direction. Okay. Let us understand what these blocks are representing. These blocks are basically saying, depending on the type of particles, their mass, their energy, their charge states, their nature of interaction with the matter, you need to arrange different type of detection mechanism. First of all, tracker. What does this tracker means? A particle is entering into it. It will not going to disturb the particle much. It will just sort of take a sample out of the particle body and let the particle do whatever it wanted to do. How, which way one can do? Just apply a magnetic field, check how much bending it is facing, and from this bending you can have the information about its momentum, or sometimes identity as well. So here, please keep in mind that tracker means minimum amount of disturbance in terms of its energy. So particle, as it is coming with some energy, the energy it will be leaving your tracker should be with the same energy. But practically it is not possible. Sometimes it will face some small amount of energy loss, and from this energy loss probably you will detect it. But in some cases where you don't want this energy loss to be there, then you can use some electromagnetic arrangement where particle will bend and leave some information. Okay. So tracker means energetically you are not hampering the particle you want to detect. Okay. So what informations this tracker will give? Probably this m by q. I have some information about this, about the m by q, mass by charge, probably the momentum, these two, but not the energy. Then comes EM-cal, electromagnetic calorimeter. As the name suggests, it will be there to measure the energy. Energy of which kind of particle? For those particles which are active electromagnetically, so which will interact with the matter in electromagnetic channels. And the examples are electron and photons primarily. Okay, so for if you have electrons and photons in your these particle samples and you want to detect, you have to arrange a electromagnetic kind of calorimeter. Okay, and then and calorimeter by itself, it is a destructive means of measurement. What is the destructive means? Once the particle enters, then I mean complete amount of the energy of this particle will be absorbed. So essentially particle will be absorbed within this block, and this particle cannot leave after this electromagnetic calorimeter. So you are destroying it. So you are measuring something by destroying it completely. So what kind of information electromagnetic calorimeter can give? Depending on the design you have adopted for this calorimeter, you can get momentum information as well as the energy. Okay. And then comes the H-cal. This H-cal is the hadronic calorimeter. Why it is sitting after electromagnetic calorimeter? Because the chance of nuclear interaction is less probable compared to electromagnetic interaction. Can anybody tell why? Why is the chance of nuclear interaction is less compared to electromagnetic interaction, though the nuclear interaction is stronger? Anybody? No? Okay, maybe you know, but try to, explain this. Okay. Yes, somebody is talking. Yes.
Maybe because this electrons don't interact strongly. So
what if you have a
they just
positive
have
ion?
Electromagnetic interaction.
What happens if you have a positive pion? Then pion will also interact in through strong interaction, right? Who is talking?
Yes.
Could you please tell your name?
Priyanshi.
Priyanshi. Okay, Priyanshi. Then
Priyanshi. I said Tirupati. Yeah.
Okay. Any clue that if a positive
yeah,
pion goes?
Yes, sir.
Yeah. So okay, no problem. So issue is, see, to have a nuclear interaction, the pion or the electron, the charged particle, need to get close enough to the nucleus within the subatomic domain. But to interact through electromagnetic interaction, it just need to enter the atomic domain, right? Now, if you take the ratio of the area taking subatomic distance and atomic distance, you will find why the cross sections are less for nuclear interaction for charged particle and why the electromagnetic interaction is more probable. Okay, you can calculate it. Take it as a very small homework for you. Okay, so at least it is clear that hadronic interaction and then so that's why people always try to keep hadronic calorimeter after electromagnetic calorimeter when you have a complex setup for the experiment. And see, just at the end I have kept muon, because muons are the least interacting particles. Probably already Professor Shao has told you about this muons characteristics. So that's why it is less probable muon to leave any substantial footprint in the tracker. It will not going to create substantial amount of information in the EM-cal and neither in H-cal. Probably it might have left substantial amount of information either of this block if they would of infinite extension. But in experiment you never expect any detector to extend to infinity. That's why expectation is muon will least interact with all these earlier three blocks and pass through the whole detection stacks. That's why you need to have an arrangement, very high power arrangement. High power, by high power means which can resist anything, which can stop anything. Very hard material or very dense material, so that muon which was not getting muon last one. Now, can anybody tell that what happened if we put all these blocks in reverse? First muon, then H-cal, then EM-cal, then tracker. Will it work? Okay, no, because to detect muon, you have very high dense and very thick block. If you place the muon in the beginning, then everything will be absorbed. Nothing will be left, I mean, after this muon block. So nothing nothing is there after this muon block. That's why, I mean, all the information lost. So during stacking of this or arranging this kind of detectors, you need to be careful. I mean, which one you are putting close to the particle source and which you have to put far away from the this detector, particle source. So these information is equally important when you are, designing a complex experiment. Okay, good. And this is not a very much schematic of a complex experiment I am talking about. This really exists, and I have taken one such example. This is the example, I have borrowed from CMS, cross-sectional view of the very much complex experiment that CMS had. So see here, if you look at the this picture closely, you will find that at the center this particle source is there, and this particle can come in any direction. That's why a conical kind of section has been shown here. Actually, it is extended in all 4 pi. Okay. Then at the beginning, these lines, it actually represents a tracker. So in this tracker, basically a sort of magnetic field, arrangement of magnetic field and electric field. When particle passes through it, it will bend slightly and leave some informations to get the momentum and the direction information. Okay. And then followed by this is a electromagnetic calorimeter, as I was talking in the earlier page. And after that, a hadronic calorimeter. And just a very small but very important information. Look at the extension of the, comparative extension of the electromagnetic calorimeter and the hadronic calorimeter. You will find at least 10 times thicker will be the hadronic calorimeter compared to the electromagnetic counterpart. Why? Because of the same reason. Probability of hadronic interaction is very much less compared to electromagnetic interaction. That's why to have substantial amount of interaction, you need to extend the material block. That's why hadronic calorimeter are always extended compared to electromagnetic part. And later on, you can put muon for CMS. There is no such muon detector. That's why there is none. Okay. Okay. So we know about what is simple and what is complex detector. As I was saying, particle source for us, if we keep in mind it's a RIC or LHC type of experiment, then we are expecting to have a collision. So two oppositely moving beam will collide at some point, this red extension, starlight. So there they will collide, and depending on the amount of energy available, lot of particles will be coming from there, and they will be moving in any direction, any 4 pi direction. So what should be the ideal configuration for the detector stack of the complex experiment? You can imagine it should be a spherical cell. So your detector should be such that they will fit at one point of this spherical cell and arrange them one behind other. Okay. But believe me, if you are really doing this, even if you have participated in any small scale experiment, making this spherical cell for complex experiment where you have more than one detectors and you have to take connections out, you have to support them, you have to make arrangement for cooling and so on. This spherical cell kind of structure is very difficult, both to hold and to stack them. Okay. And what could be the closest and close geometry to this spherical cell? It could be a cylindrical one, right? So this is the practical close resemblance to this spherical cell when you have a collision of two oppositely moving beam. So by this cylindrical cell, you will cover all 4 pi directions. Also, it will be a little bit easier, supporting them. Since this end part are open, you can have electronics or other mechanical arrangements coming out from there. or if you have some connections need to be taken out, they can be taken out from the top or bottom, and so on. And this is exactly the reason, if you look at any of the complex experiment of present this high energy physics domain, they are all like a cylindrical shape. So different type of detectors, they are stacked together in onion like structure, one after other, in a cylindrical structure, along with two detectors from the packed them from the two side. So those are called end-cap detector. Okay. So here, when you have a cylindrical type of this detector stack, we usually define different domain with this name: central domain and forward domain. So ideally, one should be forward and one should be backward. But usually we talk in terms of rapidity. So in terms of rapidity, about this zero, this center, this is the central part, and either side from this central part is the forward. Okay. Okay, good. So now let us look at the Alice experiment. What is Alice? So whenever somebody asks, what is your name? Who are you? Then it is obvious that you should tell your name and a little bit more about yourself, so that the person in front of you recognize you afterwards, or at least know a little bit about you in detail. And that is the exact motivation behind giving this picture and few of the information in this slide. So the left hand side, I have shown the schematic of the Alice experiment. See, it's a cylindrical type, right? And different type of detectors are stacked together, starting from the very inner cylinder, then after that there is a middle one, and outermost there is something else in red color. If you talk about the dimension of this detector, whole detector, it is 16-meter height. It is 16-meter height, 26-meter long, and 16-meter wide as well. Okay, so we can think that how big is the detector, and you can compare looking at the two persons just standing in front of the detector, how much big this detector usually are. Okay, when you have some system and want to describe it, it is necessary to have the coordinate system, and Alice also do have. And what is the this axis system? Just look at this particle source, yellow with a red star-like boundary. I have taken it out at the bottom and try to sketch the axis, different axis. So Z axis is the axis along the beam. So two beam are colliding. This beam path is itself the Z axis. Okay. And from this beam, okay, so this beam is the Z axis. Now at the collision, if you draw a perpendicular cross sections, then the axis going upward or downward, this is the y axis, and it is positive in the upward direction, negative in the downward direction. And what about the x axis? This is either it is going to the left or the right. So when it is going to the left, this is the positive, and when it is in the right, it is negative. There are other way of identify them. Other way of calling them. This I side, A side, and U side. I have put these words as well on that. On the side of this axis. What does the mean? This I side means if you are walking if you are walking along the beam, and if the center of the ring, LHC ring is at the center at your left, then the direction of your movement is the positive Z, and direction of your head is the positive Y, and the left side towards the center of the LHC ring is the inner side, eye side. Okay. Now let us try to find some very catchy information or useful information rather. What is the weight of this very big complex detector? This is about 10 to the 7 kg. It's very big, very weighty. And it is 56 meters below the ground level. And it is close by to the Saint Denis Poli village. It is in the France side. And I mean, 7-8 kilometers away from the actual sun site. And what is the food it needs? 10 megawatt a year. It is about 10% of the total sun consumption. And usually sun on an average 200 megawatt a year consumes, which is exactly need to light the whole Geneva city. So we can imagine how much power the sun consumes, and our experiment, this ALICE consume. So how big is this? What amount of energy is spent to run this kind of a complex detector? Not only this, the design for this complex detector ALICE is such it can handle up to interaction rate for lead-lead collision, heavy ion collision, 7 to 10 kilohertz. Probably interaction rate and what is the difference between PP collision, lead-lead collisions, it will be much more explicitly explained by Professor Shao in his class. So let me take it as granted that you know all these things. This means it is the interaction rate is quite high for lead-lead collision, and this complex experiment can handle this very high rate. Okay, but not this 7 to 10 kilohertz ALICE can handle. It is limited by one of its detector, which is the heart of the detector, TPC. It can handle maximum up to 3.5 kilohertz. That's why ALICE can handle up to maximum 3.5 kilohertz, but it can collect data for interaction rate 1 kilohertz limit. Okay, and the collected luminosity, as I was talking at the very beginning, it can handle is up to 1 nanobarn. Okay, so at least you have some information about the ALICE. If somebody tells you that okay, I want to propose a detector for ALICE, at least you have something in mind that ALICE is something like this. If somebody is talking about a detector, it should fulfill this kind of purposes, or it should at par of the existing detector which can handle this kind of interaction rate or luminosity. Okay, so now this is again the ALICE experiment, the same picture but in much more scientific way of representing it, this right hand side figure. So this is in terms of rapidity, rather it's a pseudo rapidity. So if you look at the this figure, the way detectors are stacked in the cylindrical this cell, you can see the whole rapidity range more or less are populated. So it is assured that ALICE experiment is designed in such a way it will not going to lose many of the particles, rather it will catch all of them. The extension is almost in 4 pi direction. Okay, and then comes the physics goal. What is the primary physics goal for these detectors? Primary physics goal is the initial phase of matter, to study the initial phase of matter at very high temperature and density. And how will we do it? There are different features that one can probe, starting from this say global event features like multiplicity, rapidity, and so on, evolution of emitting source, how it is evolving with time and space, degrees of freedom versus temperatures, just to know whether they are in hadronic form or to this partonic form, and if they are in partonic form, how they are behaving, and so on. Then chiral symmetry restorations, some particle ratios, collective effects from correlation of different particles, and hard probes like jets and so on. These are the main features that will be very much important, and ALICE is studying and will study to know more about the initial state of matter. And how will you do it? Just a little bit, few more words. Global event features, multiplicity, and rapidity distribution. And from there, you can have some idea about centrality and initial energy density. Just I'm talking this, just take this as information. There is a need for, passing this information. And then for evolution of emitting source and degrees of freedom, these are done using multi-particle momentum correlation and by this PT spectra and particle ratios. And PT spectra and particle ratios, keep in mind. And then this non-statistical fluctuations, critical behavior or and chiral symmetry restoration, how people do by E/E analysis for spectra and particle ratios. Distortions of this difference between this gamma and charged particle give you some information about the DCC. So you need to measure this number of photons and number of charged particles. And chiral symmetry restoration can be studied using resonance decays. What next? Next is the collective effects and hard probes. And they are there. I mean, one can study them using elliptic and directive flow from correlation studies, of course. And hard probes, by means of hard probes, very high PT particles like heavy flavor or jets, to be specific. What is the motive behind, passing all these informations in a detector class? There's a need for it. So whatever we have discussed so far, different kind of features, if you summarize them, there will be only three things you can end up. One is masses and charge states of different particles you need to measure. Either particle ratio, PT spectra, type of particle, correlation between two particles, whatever it may be, you need to know the mass and the charge states, particle identification. And then their momentum, how fast they are moving. And last one is the energy measurement. Energy measurement could be done in full or partially. If you are doing partially, then you have to calibrate it to get the whole information. But these days, people prefer to have full energy information. Okay, so these three categories one can summarize in more concise way, like PID, particle identification, tracking, knowing the momentum, and calorimeters, knowing their energy. And that's all. In any experiment, if you have these, three informations, PID, tracking, calorimeters, you are done. You are ready to do the analysis. Few more words about these informations, this summary. The take-home message is very clear. You need to have some detection mechanism which cannot be a single one. They may be different. So we have to find a way to have more number of detectors which will work in different way, but they should work in synchronization. Okay, and then the important part is detector to be stacked in such a way not to miss a single information, if possible. So, and this brings the concept of onion-like structure. For in this case, it's a cylindrical one, in cylindrical shape, onion-like structure, but in cylindrical shape. Okay. Okay. So once you are familiar with these informations, next one is the what kind of technique one should think of. One is charge particle. You have to measure charge particle, and charge particle could be light or heavy, and also neutral particles like photons and neutrons and so on. You need to measure momentum, and momentum could be starting from say MeV to GeV range. And as I was saying, technique should be different. Then energy is again starting from MeV to GeV. Even if you have calorimeters, same type of technology might not be useful to work with equal efficiency for this much wide range of energy. And particle identification, of course. So our idea is to have mass, charge, momentum, and energy. Just before going to have other thing, the very important thing to build a detector is how they will interact with matter. The particles you want to detect, how they will interact with matter. Okay. Light and charge particle, they will, the most important part for high energy sector is the Cherenkov radiation, Bremsstrahlung, transition radiation, and hadron scattering. These are the very specific type of interactions which are used to detect them. Okay. And for photons and neutral particles, most important part are the pair production and hadronic shower. Apart from these other interactions, those are there in this list. They are also important in a sense. When a particle passes through a block, they will deposit some amount of energy because of collision, and these collisions could be because of, say, Compton scattering, say Thomson scattering, say something else. So all those elastic, inelastic, everything are listed here. So these, different, interactions with different colors, I have make it different just to make you, comfortable that get this information that these specific interactions are used to build a specific type of detectors. Okay. Then what is the methodology? What is the way these particles are detected? Very simple. You have a block of material, let a particle pass through the block, it will lose some energy, right? Some amount of energy. So it entered with energy E, and it will, coming out with energy E minus delta E. And this delta E amount of energy will be stored in this block. And this energy, can produce a light signal if it is a scintillator type of thing, or it can produce a charge, charge ion pair, electron ion pair, right? And this electron ion pair charge, they could be a signal, or if it is a light, you can convert this light using a photomultiplier, where this light will fall and produce electrons. Again, you will end up with the electrical charge. So ultimately, at the end, you will be end up with a current, charge current. Okay. So this current is the signal to you. So some particle passed through a block, lost some energy, very small amount of energy. This is arising as a current pulse, and you are measuring this current pulse. This pulse has height, width, and etc., lifetime, etc. So measuring them, you can have some information about the delta E, delta X. And once you have this information, you can go back to the Bethe block formula, try to fit for which particle it is matching, and have some information about its momentum or particle identity. This is the simple, very simple, very simple methods that one can apply to build a PID type detector, tracker type detector, or calorimeter. Okay. Then comes the gas detector. As I have started with this gas, very simple detector. When I was discussing about simple detector, this is a very simple detector, gas detector. A tube with anode wire passing through the central axis filled with gas. If you, change the applied voltage along the x-axis, and measure the charge produced when a particle enters, ionizes the gas, then probably we will find this kind of curve as shown in the right side. Alpha particle will show little more energy deposition. That's why more number of charge particles produced, charge carriers produced. Beta little less, and gamma even less. Just concentrate on the proportional region. This proportional region is very much important in a sense. It can, just looking at the energy deposition, show the number of carriers. Just looking at the number of carriers or looking at the current, you can go back to the number of carriers or go back to the dEdx. You can have information whether it is by alpha or beta or gamma or some other particle. So if you make this gas detector in such a way, apply your voltage in such a way, tune your gas density and other things in such a way that it will act, it will work in the proportional region, you are in a very safe domain to identify particles, measure their energy. And if you look at each individual curve, they are more or less linear. So the detector is also working linear. So your output is directly related to the input energy deposition, and so the incident energy. And using this very simple mechanism, people has developed a very, state-of-art detector, which is known as multi-wire proportional counter. At the left top, this is I have shown three plane. The top and the bottom is serving the purpose of cathode, two plane. foil type plane, and the middle one is a mesh, wire mesh. It could be a, I mean, one-dimensional mesh, or could be a two-dimensional. So let us assume it's a one-dimensional, two-dimensional, then they should not touch each other. There's a other way. Let us take the simplest one. So a one-dimensional mesh inserted inside, and it is serving the anode just like the central wire in case of cylindrical tube. And when the particle enters, then it will produce ionization, and each wire in the central mesh will act like one proportional counter. How it is assured? Look at the field line structure at the bottom of this schematic. See, once particle enters, I mean, all these wires, they are, as far as the electric fields are concerned, they are completely separated. There is no interconnections. So once particle is creating ionization in one of the electric field region, then it will go to the corresponding wire. So ultimately, you know the position, right? Which wire getting signal from there, you know what is the XY value. Now, if you modify this arrangement a little bit in a more sophisticated manner, just roll this paper-like 3-layer stack into a cylinder, you will end up with this middle picture, which is exactly the a very important detector used in Alice experiment. This is called time projection chamber. And here you have, instead of this, I mean, this wire mesh at the middle, they put this wire mesh at the end cap, and put the cathode plane at the middle. Okay. And this way, basically, this middle one, this is a combination of two detectors. This MWPC that I have just told you, along with a deep chamber. Deep chamber also act, on the principle of gas detector. So combining these two, why what combining? Because from MWPC, you know the XY position, and if you use dipped chamber, information, then you will have information about the Z axis from the time. Okay. Okay. So, and the characteristics to be noted in case of MWPC are limitations in 2-stack resolution, high material budget, and most important is the lower rate capability because of ion backflow. What is the ion backflow? When a charge particle enters, it will produce electrons and the ions. This ion will move towards the cathode, and its mobility is less. They will last. I mean, they will be there for long, and it will decrease the electric field, and also, the density of the gas will be disturbed, and so on. Because of this, the detector dead time, detector busy time will be increasing. That's why this rate capability is an issue for MWPC. But in Alice TPC, there is a way to overcome a little bit. Then, how to increase this rate capability using the same technology of gas detector? This is the GEM, gas electron multiplier. So instead of using a mesh, wire mesh, you use a dielectric material, very thin dielectric material coated with conductive, very thin conductive plane from both sides, top and bottom, and place them, insert them between these two cathode plane. Make holes in a regular pattern on this middle layer, and apply voltage across this two coating, top and bottom coating. What you will find, instead of field lines all through, you will only have field lines through these holes, as shown in the middle right picture, and these field lines are very intense through the holes and very light when you are out of this middle layer. Okay, so here, when the charge particle enters, it will create a charge, and then a tiny cluster will be produced when it is passing through these holes, and it will be collected. There is no question of this ion backflow and all these things, and it will be really fast. And this is the methodology people are adopting to apply in the present upgrade of this Alice experiment. Why I am, spending so much amount of time about these detectors and all these things? There's a reason. In the next class, what we wanted to, wanted to discuss is just about the extension, the purpose, and segmentations, where it is placed, how it is working, and all these things for the Alice detector. Since you know about the methodology, at least when I will be saying it's a TPC with MWTC, you know that how TPC is working. If I say no, it's a TPC with GEM, you again know that, okay, it's now GEM, it means its rate capability is very high. It can handle much more interactions, which is desirable in run 3 of LHC data taking. Or if I talking about some other tracker which is with which is using solid state detector, then you have to understand in terms of some other active medium like silicon or scintillator. That probably I will discuss tomorrow. So if any there is any questions, please let me know.
Sir, yes. I am Hirok from Jadavpur. Can you go to
yes.
slide number 8?
Can you tell once more your name?
I am Hirok from Jadavpur University.
Acha, Hirok. Okay. Yes. Yes, Hirok.
Yes, sir. This slide. In the left hand side, you mentioned that the rapidity region, this is forward. In the left hand side.
Yeah.
Why yes. Is it so? Can we tell it
so,
as a backward rapidity region?
Yeah. You can say it's a backward, but the nomenclature is, rapidity actually starts from, say, the way we measure this rapidity is something like this. So starting from 0 to say 10, you will have same thing, 0 to -10. If you have a symmetrical, beam colliding, then going either to the right or to the left doesn't make any difference. And this is usually the case in case of LHC run, except in the fact of this P-led collision. When you have a asymmetric type of collision, then of course this has a meaning, whether your detector is placed in the forward direction or in the backward direction. But if you have a symmetric type of collisions, lead or PP, then there is no difference. And in that sense, people always used to call it a forward instead of backward. Okay.
Okay, sir. It is actually with respect to the colliding particles.
Exactly. So what kind of things you are studying? Had it been a case, say, you are designing for a fixed target experiment, then of course this backward and forward does have, tremendous meaning, but not in case of collision when you have a symmetric collision. Okay.
Okay, sir.
Yeah.
Thank you, sir.
Yes. Yes. Anything else? I know these are very simple, and most of you know these things, I guess.
Sir.
Yes. Who is there?
Hello.
Yes. Who is there?
Yes. This is Priyanshi again.
Yeah.
So I had a naive question. So
yes.
Since there are these holes in that gem detector, so does the spacing between the hole curb the measurement process in any sense? Because they determine how close particles to each other can be detected.
Exactly. So your question is very much valid. So if you look at the particle density, what you are expecting from your collision at a particular distance, you know how to calculate the particle density, right? By means of particle density, I mean how many particles you are expecting in 1 centimeter square area, right? So if you are saying, say, 2 particles you are expecting in 1 centimeter square area. Now, if you look at this gem, probably I will be talking about when I will talk about Alice TPC. These holes are spaced about, say, 140 micron meter away. So very close by holes. Okay. So you will find
okay.
At least 100 holes in 1 centimeter square area. So we are expecting 2 particles to reach in 1 centimeter square area, and you are designing your detector to have 100 holes. So only 2% occupancy. So it is very unlikely that you will going to miss either of them. If you are really, I mean, unfortunate, then probably one of them can, I mean, 2 of them can go through the same hole, or one of them can hit between the 2 holes. That could happen, but those are very, I mean, those are rare cases, and you have to, I mean, you have to live with it.
Okay.
Yes.
Okay.
Okay. Okay.
And just another question. So in most of these TPCs across, they use the noble gases, xenon or argon or thing. So why are we still using? Why do we use noble gases particularly, even though we know that like they are the least reactive things to the incoming particles?
One thing I can think of is the chemical inertness. So this chemically they are inert, so they will not going to interact among themselves. And second one is the, I mean, you want, I mean, say, so if the, say, this ionization potential is less, and if you have some background kind of excitations, it can initiate the ionization, right? And the second thing, but you don't want that.
Yes.
When a charged particle is coming and you want, I mean, really that charged particle of particular energy to heat substantially the molecule and, I mean, give the ionization, not a background thing. So if your ionization potential is very less, it is little bit, I mean, little bit risky to use. This is one thing. Another thing is inertness. Anything more you?
Okay. Okay.
More? Yeah.
Thank you. Thank you.
Yeah. Any more questions, comments, or more information you want to share with all of us? No? Siddharthji?
Yes, Sanjibji. Sanjibji. So I think,
seems,
yeah, looks like there are no more questions. So
okay.